All right, hey folks, continuing on with our study of infinite series. Section 10.6, we're going to look at alternating series. So far, almost every series we've looked at, we have seen series that exclusively had positive terms. Well, things are about to change. We're going to relax this and we're going to expand our repertoire of series we can analyze. And we do that by looking at what is known as an alternating series. Now, an alternating series is a series where the signs of the terms alternate. In other words, every other term, the signs will alternate. So the signs would either go positive, negative, etc., or negative, positive, etc. Those are alternating series. If you encounter a series where the terms go positive, negative, 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 etc., that is not an alternating series. An alternating series is a series where the signs of the terms, successive terms, will alternate between positive and negative. So here's an example of an alternating series. It's actually an alternating geometric series. So notice how I could write it as n equals 0 to infinity, negative 1/3 to the n. We're going to want to see that as an alternating series, which is why I've written it the second way. The sum n equals 0 to infinity, negative 1 to the n times 1/3 to the n. Keep in mind, I'm once again using old rules of exponents to rewrite negative 1/3 to the n as negative 1 to the n times the quantity 1/3 to the n. Now the terms of the series, well, let's look at the terms of the series. It doesn't matter how we write it. Starting off at n equals 0, the terms of the series are positive 1, minus 1/3, plus 1/9, minus 1/27, plus, minus, yada, yada, yada. So notice how the terms of the series, successive terms, alternate in sign. That is what makes this an alternating series. So here's how we'll know if an alternating series converges. First off, a sub n greater than 0. Then the alternating series, which has the following forms, n equals 1 to infinity. We could write an alternating series, or an alternating series could appear as negative 1 to the n times a sub n. Or the alternating series could appear as negative 1 to the n plus 1 times a sub n, or negative 1 to the n minus 1 a sub n. So whether or not the part that makes it alternating is the negative 1 to the n, or negative 1 to the n plus 1, or negative 1 to the n minus 1. The a sub n, that's going to be one of the key parts. So here's how we know if that alternating series converges. First, the limit as n goes to infinity of a sub n must equal 0. Notice how the alternating series test, in condition 1 here, notice how that's what we really have embedded in here is the nth term test for divergence. So there's nothing new there. Let's see what the next condition is. A sub n plus 1 is less than or equal to a sub n for all values of n. Well, that's just saying that the terms are decreasing. A sub n plus 1 less than or equal to a sub n. That means a sub n, the sequence that is defining the terms of the series, is decreasing. That's really nothing new either. And that's it. Those are the only two conditions that have to be satisfied in order for an alternating series to converge. That's it. If you violate either one of those two conditions, then the alternating series diverges. So, it's time to go look at an example to see what's up with these alternating series. So part A, we're going to analyze the alternating series negative 1 to the n plus 1. times 1 over 2n minus 1. Part B, we're going to, well, first we're probably going to have to write the series notation for 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus minus yada, yada, yada. Kind of looks familiar to me. It kind of looks to me, that series, it looks like the harmonic series, but the signs are alternating. Yeah, once we get the series notation for part B, we're going to end up calling that the alternating harmonic series, which will be a very important series to know. And then, oh, here's a couple more. We're going to do an example. The series -1 to the n plus 1 times n over 2n minus 1. And in part D, it'll be the series -1 to the n plus 1 times the quantity 3n plus 2 over 4n squared minus 3. So you know what it's time to do. Make sure you have this example written down in your notes because I'm going to head off to the chalkboard and work out each one of them. All right, this example we were asked to determine if the following series converge or diverge. I know there were 4 of them. I'm just going to put them up here 2 at a time. So the first one was the series n equals 1 to infinity, -1 to the n plus 1 times 1 over 2n minus 1. So the first thing to be aware of is in this alternating series stuff, the 1 over 2n minus 1, that's the a sub n. So remember, there were 2 conditions that have to be satisfied in order for an alternating series to converge. So we just have to analyze those 2 conditions. Violate any one of those 2 conditions, it diverges. So here's the first condition. The limit as n goes to infinity of a sub n. Well, that's a sub n. Well, as n goes to infinity, I think this is a pretty easy limit. You know, we immediately see the limit is 1, or I'm sorry, the limit is 0. So we've satisfied condition 1. And remember, this is really just the nth term test for divergence that's built into the alternating series test. Condition 2 is a sub n plus 1. Remember, that's a sub n. Is that less than or equal to a sub n? Well, remember, a sub n plus 1 is nothing more than just putting n plus 1 into the n here. So you'd have 1 over 2 times n plus 1 minus 1, less than or equal to 1 over 2n minus 1. Yeah, so maybe I should put a question mark there. Is that true? Well, let's clean up this denominator. You know, distribute the 2. So you'd have 1 over, let's see, 2n plus 2. So 2n plus 2 minus 1. That's 2n, see, plus 2 minus 1. That's 2n plus 1. How do I know this inequality is true? That's right, it's our denominator argument. The numerators are the same. This denominator is going to be larger than this denominator, so this fraction is definitely less than or equal to this fraction. So because of the denominator argument here, we know a sub n plus 1 is less than or equal to a sub n. That tells us the terms are decreasing. So we know this is true. This was true. We know this is true. Our conclusion, the series -1 to the n plus 1, 1 over 2n minus 1, it converges thanks to the alternating series test. Converges, alternating series test. So let's go check out part B here. Our first task in part B is to rewrite this into series notation. And as I mentioned on the slide, it looks to me like this series is nothing more than the harmonic series, but with alternating signs. So this is the alternating harmonic series. So we need to come up with sigma notation for this. So we know the harmonic series is a 1 over n. Well, what's the exponent going to be? Is it going to be n plus 1? Well, the first term is positive 1. So, when 1 goes in here for n, that'll be a 1. We have to make sure negative 1 to whatever the exponent is kicks out a positive 1. N wouldn't do it. Because if n were 1, this would be a negative 1. Negative 1 times 1 is negative 1. We want that first term to be a positive 1. So it looks like it's negative 1 to the n plus 1. So first, before we go on and analyze this, I need you to remember that this is the alternating harmonic series. It'll be just as important to remember as what the harmonic series was. So you remember the harmonic series? I told you way back when with the harmonic series, it was going to be important to know it by name and to know that it diverges. It's going to be just as important to know this series by name. And now let's see if it converges or diverges. We crank it through the alternating series test. So part 1. The limit as n goes to infinity of a sub n. Well, we know that limit is 0, so it satisfies the first condition of the alternating series test. Condition 2 is a sub n plus 1 less than or equal to a sub n. Well, a sub n plus 1 is just 1 over n plus 1. A sub n is 1 over n. We know this is a true statement because of the denominator argument. So is a sub n plus 1 less than or equal to a sub n? Yes. That tells us our alternating harmonic series. We know it converges. And we know that thanks to the alternating series test. So file that away. That's an important one to know its name. That's the alternating harmonic series. And to know the alternating harmonic series converges. File that away. All right, there were two more parts to this example. So I got to do a little erasing on the board. So as I'm erasing the board here, talk amongst yourselves to get part C and part D up here. So part C was the series n equals 1 to infinity, negative 1 to the n plus 1, n over 2n minus 1. That looks awfully familiar to what part A was. And the series in D, n equals 1 to infinity, negative 1 to the n plus 1, then a 3n plus 2 over a 4n squared minus 2. All right, here we have alternating series. Let's start off cranking it through the alternating series test. Part 1. The limit as n goes to infinity, n over 2n minus 1. All right, so trying to find that limit, I would divide everything in the numerator and everything in the denominator by n. So I get 1 over 2 minus 1 over n. And this limit, that limit is 1/2. It is not 0. That tells me, I'm done. That tells me the series diverges via the alternating series test. Don't have to go any further. All right, D. Oh boy, look at this. Negative 1 to the n plus 1 times 3n plus 2 over 4n squared minus 1. It's an alternating series. So we start off cranking it through the alternating series test. So the first thing, the limit as n goes to infinity, 3n plus 2 over 4n squared minus 2. So in trying to find that limit, I would start off by dividing everything in the numerator and everything in the denominator by n squared. So that gives me limit as n goes to infinity, 3 over n plus 2 over n squared, all over 4 minus 2 over n squared. Then as n goes to infinity, that's 0, that's 0, that's 4, that's 0, 0 over 4, 0. So now we need to move to part 2. Remember, part 2 is a sub n plus 1 less than or equal to a sub n. And now look at this. I'm gonna babble and look at the same time. A sub n plus 1. So I'd be putting n plus 1s in for the n here. Is that less than or equal to a sub n? That looks like it's going to be some ugly, messy algebra. It doesn't look nearly as friendly, well, as the one we did in part A or the part B, the alternating harmonic series. So I just think it looks a little too ugly. So you know what I'm going to do? What we did way back at the beginning of the chapter. Let's look at the function of the reals. 3x plus 2 over 4x squared minus 2. And let's see what's happening with this function of the reals. Remember, as long as the function of the reals and the function of the positive integers, as long as they agree for all positive integers, whatever this function of the reals is doing, the function of the positive integers is doing the exact same thing. It's along for the ride. So we can analyze this function of the reals. So get the derivative of this function, and I get the derivative to be negative 12x squared minus 16x minus 9 all over 4x squared minus, I think I have a typo here. I do. I don't have a typo. I have a typo on the board. When I wrote the series down originally, I made a mistake. You probably all noticed. That should have been a minus 3, not a minus 2. So let me go back and change that now. It's not going to affect anything that I've done so far. You know, it just makes that a 3, makes this a 3. That limit is still 0. It just makes this a 3. It hasn't changed anything. I could have left it alone, but that's what was on the slide, so I apologize for writing it down incorrectly. All right, so here, make sure you do get this as the derivative. So when I look at this derivative, you know, maybe I'll do one little step of simplifying. In the numerator, factor out a negative. Keep in mind, folks, we only care about looking at this function of the reals on the interval 1 to infinity, because that's where our sequence is defined, 1 to infinity. So we're only looking at this function of the reals on the interval 1 to infinity. So no matter what real number you pick in the interval 1 to infinity, and you toss it in for x into the derivative, well, the denominator is always positive. any real number that comes in here for x is going to produce a positive number inside the parentheses. The opposite of a positive is negative, and the denominator is always positive. So negative divided by a positive is negative. So on the interval 1 to infinity, the derivative is always negative. That tells you the function is always decreasing. Because the function of the reals is always decreasing, that tells us a sub n is monotonic. It's decreasing as well. And if a sub n is decreasing, that tells you, oh, this is a lot of fun. That's what it means to be decreasing for a sequence. A sub n plus 1 is less than or equal to a sub n. So the limit was 0. We have now shown that a sub n plus 1 is less than or equal to a sub n. So what does that mean? That means that our series converges thanks to the alternating series test. All right, I have a couple here I'd like you to practice right now to make sure you're seeing how friendly the alternating series test is. So in section 10.6, go to the exercises, and right now I would like you to work number 16 and number 22. All right, so you know what to do. Pause the video, go work number 16 and number 22. Once you've done those two, restart the video. I'll be here at the board cranking through them. All right, folks, here we go. Number 16, you had the series n equals 0 to infinity, negative 1 to the n. I believe the book had it written as negative 1 to the n over n squared plus 10. I went ahead and just did the first step and wrote it as negative 1 to the n times 1 over n squared plus 10. That way I can easily see what the a sub n is. So let's crank it through the alternating series test. The first thing we check, the limit as n goes to infinity, 1 over n squared plus 10. Clearly that limit is 0. So now we check the second part of the alternating series test. And the second part, remember, is a sub n plus 1 less than or equal to a sub n. Well, a sub n plus 1 is 1 over n plus 1 squared plus 10. And so we look at this inequality. You know what? I think I can easily claim this inequality is true. It's the denominator argument. This denominator is always going to be larger than this denominator. So this is true. A sub n plus 1 is less than or equal to a sub n. So that tells us that the alternating series, negative 1 to the n times 1 over n squared plus 10, it converges thanks to the alternating series test. All right, now number 22. This one starts to get a little bit more, this one gets a little more fun because I see a cosine of pi n. So it's kind of like something is disguised here. So, look at what is disguised here. That, let me just come over here to the side. We're starting at an n value of 1. I'm just looking at that cosine pi n. So for n equals 1, it would be cosine of pi. For n equals 2, it'd be the cosine of 2 pi. For n equals 3, it'd be the cosine of 3 pi. I have just enough room to write down when n equals 4, it'd be the cosine of 4 pi. We can do this. We know this. We're unit circle gurus. We know the cosine of pi is negative 1. The cosine of 2 pi is 1. The cosine of 3 pi, negative 1. The cosine of 4 pi, we know that's 1. So negative 1, 1, negative 1, 1. That's an alternating series. This is an alternating series. So really, this piece right here was disguising the negative 1, 1, negative 1, 1. But even though it was disguising that, I can rewrite the series. Instead of seeing the cosine of pi n, I should be able to rewrite it so that I have a negative 1 to some power. So let's see. I'm going to just write down this negative 1. I'm going to leave the power off for a moment. So instead of cosine pi n, well, let's look. We wrote down what would happen for n equals 1, n equals 2, n equals 3, n equals 4. It's going to produce a negative 1, a 1, negative 1, 1 for 1, 2, 3, and 4 respectively. So what must my exponent be here? So when I start at 1, I go negative 1, and then for n equals 2, I get positive 1, and then for n equals 3, I get negative 1. That's it. That's it. It would just be the nth power. So the series is being rewritten into a more user-friendly form for us to analyze it using the alternating series test. And the alternating series test says, first, check the limit as n goes to infinity of 1 over n squared. Very quick, we know that that limit is 0. Second, is a sub n plus 1 less than or equal to a sub n? Well, a sub n plus 1 is 1 over n plus 1 squared. A sub n is just 1 over n squared. Is that inequality true or false? Yeah, you know it's true, thanks to that denominator argument. So our series that we are originally given, cosine of pi n over n squared, we know it converges thanks to the alternating series test. All right, folks, so hopefully you're able to get number 16, number 22, and you're seeing just how friendly the alternating series test is in determining if the alternating series converges or diverges. So, let's head back to the slides and see what's next. All right, after seeing those 4 examples and doing numbers 16 and 22, hopefully you see how friendly analyzing alternating series are. Continuing on, my next question is, does the following series converge or diverge? Well, and here's the series. 1 plus 1/8 minus 1/27 plus 1/64 plus 1 over 125 minus 1 over 216 plus yada, yada, yada. Notice that this series is not an alternating series. As a result, we can't use the alternating series test. The terms of that series go positive, positive, negative, positive, positive, negative. That is not an alternating series. So does that series, the original series here at the top of the slide, does it converge or diverge? Well, as we think about that series, let me ask you another question. Does the following series converge or diverge? The series of 1 plus 1/8 plus 1/27 plus 1 over 64 plus 1 over 125 plus 1 over 216 plus yada, yada, yada. Notice that this second series I've written down, notice that it really is nothing more than saying, all right, that series at the top of the page, I'm just going to take the absolute value of each term and create a new series. So does the series of all positive terms, does it converge or diverge? Well, I think if we look at the series here more closely, we should see that it's nothing more than a p-series. That is, the series that I've written down is just 1 over n cubed. Yeah, that's a p series. And we know the p series converges. P is 3, which is greater than 1. So we know that series converges via the p series test. So doesn't it seem reasonable that the first series at the top of the slide here, doesn't it seem reasonable that it would also converge? I mean, if the series of all positive terms, the p series, converges, doesn't it make sense the series where, every third term or every second term we are subtracting? We're subtracting out a little bit. Doesn't it seem that the sum of the series at the top of the slide here would be a little bit less than the sum of the p series, 1 over n cubed? To me, it logically makes sense. But why can't the direct comparison test be used? Why can't I use the direct comparison test to say that series at the top of the slide, it converges because it's less than the p series 1 over n cubed? Well, the reason why I can't use the direct comparison test is, remember, the direct comparison test is only valid for series that have positive terms. And that series at the top of the slide here does not have positive terms. But intuitively and logically, we're thinking that series at the top of the slide will converge, because I took the absolute value of each term and came up with a p series. Because I took the absolute value of each term and came up with a p series, this gives rise to our next theorem, which is called the absolute convergence theorem. So here's the absolute convergence theorem. It's short and sweet, but man, is it powerful. If the series absolute value of a sub n converges, then the series a sub n converges. So notice what that is saying. If you take the absolute value of terms of a series and you get something that converges, well, then the series as it was given to you with some negative terms in there, it must also converge. Okay, here's a pretty important note. The converse of this theorem is big time false. The converse of that theorem is, if the series a sub n converges, I left out the word converges there, then the series of absolute value of a sub n converges. That's the converse of the theorem, and it is big time false. And to illustrate the falseness of the converse, consider the alternating harmonic series. The series n equals 1 to infinity, negative 1 to the n plus 1 times 1 over n. We have already analyzed the alternating harmonic series in this section, and we have seen that the alternating harmonic series converges. We know it converges. But if we take the absolute value of each term of the alternating harmonic series, we get the harmonic series. And we know the harmonic series diverges. That illustrates the falseness of the converse of the absolute convergence theorem. So don't try to turn it around. It's false. And always remember what the alternating harmonic series and the harmonic series are saying. Now, folks, the alternating harmonic series, the type of convergence that it has, is technically called conditional convergence. What that means is the alternating harmonic series converges as you see it, as it's given to you, under the condition as you see it. But when you take the absolute value of each term of the harmonic series, or the alternating harmonic series, you get the harmonic series, which diverges. So a conditionally convergent series is a series that converges as you see it, but when you take the absolute value of each term, you get a series that diverges. In fact, that's so important. I'm going to put it, folks, I'm going to put it in a definition. Part 1 of the definition. The series A sub n, we're going to say it is absolutely convergent if the series of absolute value of A sub n converges. So you're given a series A sub n. If you look at the absolute value of each term and it converges, the absolute value of each term, then the original series you were given is called absolutely convergent. That is the most powerful type of convergence, and it's important that you know that. Part 2 of the definition, the series that we're given is conditionally convergent if the series A sub n, so what we see as it's given to us, converges, but the series created by taking the absolute value of each term diverges. So before I go on to an example, folks, up until this section, before this section, all the series we've seen before this section, they all had positive terms. That means all of them, up until now, all of them that you said or I said, the series converged, well, they were absolutely convergent because they were all positive term series. So when you take the absolute value, you're not changing anything. Again, absolute convergence is going to be really important going forward. So let's look at a quick example. Does the following series converge or diverge? And if it converges, classify it as absolute convergence or conditional convergence. And here's the series. N equals 1 to infinity cosine n over n squared. So write it down because you know what I'm doing. I'm heading off to the chalkboard to work it out. All right, folks, now we've learned about absolute convergence and conditional convergence. And, one thing to keep in mind is that if you look at the series of absolute values of each term and that series converges, then the series as it was given to you also converges. That was the absolute convergence theorem. So here you were given a series and you're asked, does it converge or diverge? Now, if it does converge, we're going to classify it as absolute convergence or conditional convergence. Now remember, conditional convergence just means as it's given to you, it converges. But when you take the absolute value of each term, you get something that diverges. So here's the problem with the series cosine n over n squared. If you were to list some terms of the series, I'm not going to do this. You should check it. N equals 1, what the term is, then n equals 2, etc., etc. You're going to see that there are some positive terms in the series and there are some negative terms in the series. But they do not alternate. The signs do not alternate. So this isn't an alternating series. I can't crank it through the alternating series test. But we know a lot of stuff about this as it is. First, we know A sub n is cosine n over n squared. So if we take the absolute value of each term, I'll write this all out. I take the absolute value of each term. I'm taking the absolute value of each term, cosine n over n squared. Well, we know n is heading off to infinity, so I could actually go one more step here and just write this as absolute value of cosine n over n squared. I don't need to have that n squared inside absolute values. It's always going to be positive. I think we're getting somewhere. We know an awful lot about the trig functions. In fact, we know cosine n is trapped between -1 and 1. -1 and 1. Inclusively, we know that. That means absolute value of cosine n, well, its absolute value is less than or equal to 1 for all values of n. I mean, we know cosine n is trapped between this compound inequality, which is written, can be rewritten as this absolute value of inequality. I could divide both sides of this inequality by n squared. See where I'm going to go with this? That's right. I'm thinking direct comparison test. That's my A sub n. That's my B sub n. We know, come over here and write this. We know that the series 1 over n squared converges. It's a P series. P is equal to 2, which is greater than 1. We know it converges. Since we know this series converges, the direct comparison test tells us the series absolute value of cosine n over n squared, it converges thanks to the direct comparison test with the series 1 over n squared. Well, this was nothing more than the absolute value of A sub n. Because the series of taking the absolute value of each term converges, that means our original series converges. That's the absolute convergence theorem. So our original series it converges. And when we looked at the absolute value of each term, and we got a convergent series, that means we can classify this convergence. We can classify it as absolute, or we say it converges absolutely. We took the absolute value of each term, we got a convergent series, that means this series converges absolutely. Folks, absolute convergence is the most powerful type of convergence. It's what we're really going to be interested in, heading forward. When I say heading forward, I'm thinking, into chapter 11. What is so cool about absolute convergence, what makes it so powerful, is that with absolute convergence, if your series is absolutely convergent, you can mix up the terms however you want. In other words, the commutative property exists. So you can mix them up however you want and it still converges. That's not true for a series that is conditionally convergent. But I'm going to focus on the absolute convergence. Don't want to go down the rabbit hole of the conditional convergence. It's just important that when you have a series that you know converges, you know how to determine if it converges absolutely or if it converges conditionally. So this is an important concept. It's important to do. So I do have, I have 3 of them I'd like you to do. So I would like you to, in section 10.6, I would like you to do those 3 exercises, numbers 48, 52, and 59. So you know the drill. Pause the video. Do 48, 52, and 59. Once you've done those 3, restart the video, and I'll be at the board working them out. All right, here number 48. You were given the series n equals 1 to infinity of negative 1/3 to the n, and you're asked, does it converge? Does it converge absolutely? Does it converge conditionally? Or does it diverge? The first thing that pops out to me is that this looks like it's geometric in form. So right now I'm thinking, it's going to converge and it's going to converge absolutely. But I want to put in like one extra step. The ability to take this series and rewrite it so you see that it really is an alternating series is kind of important. And it's just using properties of exponents. I'd have a negative 1 to the n and then times 1/3 to the n. And we most definitely see something that looks geometric. the 1/3 to the n. So if I look at this and I take the absolute value of each term, it gives me the series n equals 1 to infinity 1/3 to the n, which we say, hey, that's a geometric series. R is 1/3, which is less than 1. We know this geometric series converges. Since this geometric series converges, and it was the absolute value of each term of the series we were given, that tells us that our series that we were given converges. And not only does it tell us that it just simply converges, it tells us it converges absolutely. Because when we took the absolute value of each term, we got a series that converges. Okay, that was a pretty friendly one. I gotta erase the board to get number 52 up here. I thought 52 might take a little bit more space, or maybe I'm just writing a little bigger today, or maybe I just need one more cup of coffee. We never know. So 52, you have the series n equals 1 to infinity, -1 to the n squared over the square root of n to the 6 plus 1. Okay, now this one looks a little different. It looks a little more challenging. If I take the absolute value of each term, so absolute value of each term, that would give me the series n equals 1 to infinity n squared over the square root of n to the 6 plus 1. When I see that series, I'm thinking, maybe I could take that series and compare it to the series n squared over the square root of n to the 6th, which the square root of n to the 6th is n cubed, and then n squared over n cubed, that simplifies to 1 over n, which we know this is the harmonic series. We know it diverges. So let's use that information to attack this. I said I'm going to compare it to this series. Specifically, it's a limit comparison test. So remember your limit comparison test. The limit as n goes to infinity, a sub n over b sub n. Okay, so now I'm gonna not write it as over b sub n. I'm gonna multiply it by the reciprocal. I'm not gonna use this version of b sub n or this one. I'm gonna use this one before I did the simplifying. And hopefully you're seeing why I'm gonna do that, because straight away n squareds will cancel out, and I have the limit as n goes to infinity of square root n to the 6th over square root n to the 6th plus 1, which I can write that using a property of radicals. I can write it like this. I can come under the radical, divide everything in the numerator and everything in the denominator by n to the 6th. And then I do this limit and I get the limit to be 1, which is finite. And it is positive. So that tells me that the series n squared over the square root of n to the 6 plus 1, it diverges. thanks to the limit comparison test, obviously I'm running out of room to write, but it's thanks to the limit comparison test with that series, which was basically a disguised version of the harmonic series. So when I take the absolute value of each term, I got a series, and that series diverges. So what does that tell me about my original series? It means right now I know it is not absolutely convergent. The only type of convergence it could have is conditional convergence. And that would mean it only converges for as we see it, as an alternating series. So that's the second thing I must do now. I must now check the alternating series test. So, alternating series test. First thing, the limit as n goes to infinity of n squared over the square root of n to the 6 plus 1. So I have to do this. So let's see, the largest power I see, well the numerator is an n squared. The largest thing I see in the denominator is square root of n to the 6th. That's n cubed. So I'm going to divide everything in the numerator and denominator by n cubed. But keep in mind when I'm dividing the denominator by n cubed, I'm going to disguise that n cubed as the square root of n to the 6th. So that gives me the limit as n goes to infinity of 1 over n. Okay, so when I take this and I divide it by the square root of n to the 6th, you know, I'd have a radical over a radical. I'm going to skip that step and I'm just going to write it as one big radical with the fraction n to the 6 plus 1 over n to the 6th, which, you know, you can write this as 1 plus 1 over n to the 6th. So then the limit would be 0 over the square root of 1 plus 0. So that's 0 over the square root 1. 0 over 1. This limit is 0. Second, so what's the second thing we need to check in our alternating series test? What we need to see is a sub n plus 1 less than or equal to a sub n. There is absolutely no way I'm going to try to do that algebraically. It just looks like it would be a mess. So for that reason, you should probably think more calculus. You should think, all right, I'm going to look at the function of the reals, which is x squared over the square root of x to the 6 plus 1. And I'm going to save this for you. I'll tell you what you need to do. You need to get the derivative. And then once you get the derivative, you need to analyze its behavior to see where the derivative is negative. That will tell you where the function is decreasing. And where the function of the reals is decreasing, that will tell you where the sequence, a sub n, is decreasing, which will then tell you if this is a true inequality. I will say that when you get the derivative, I get the derivative, and when I say get the derivative, I'm getting the derivative and I am simplifying it down as much as possible. I get the derivative to be negative x times x to the 6th minus 2 over x to the 6th plus 1 to the 3 halves. Hopefully you can read that. I don't think I've ever gone this low on the board before. So you'll get this as the derivative, and I can look at this and I can say, you know, well, this derivative is, well, it's always less than 0. It's always negative, at least on the interval we care about. The denominator is always positive. You know, this term here will always be positive. This will always be negative. Negative times positive is negative. Negative divided by a positive is negative. So this is always negative, which tells us the function, f of x, is always decreasing. Because that's always decreasing, that tells us a sub n is decreasing. And if a sub n is decreasing, that tells us this inequality is true. And because this inequality is true, we now have our final conclusion. This series, we know it converges. We know it converges via the alternating series test. As it was given to us, it converges. But it is not absolutely convergence. So it is convergent as it's given to us, which means it is convergence conditionally. It has conditional convergence. I mean, just the way I always remembered it, what conditional convergence or converges conditionally means. Under the condition as it's given to you, it converges. But when you take the absolute value of each term, you end up with something that diverges. All right, there was a lot going on here in number 52, and what, we have one more, number 59? Oh boy, well let me get my, what I call my eraser, and get number 59 written up here. 59 was kind of a cool one. I'm sure you were all excited to see 59 because it had a buddy of ours in there, a trig function, specifically an inverse trig function. So 59 was the series n equals 1 to infinity, negative 1 to the n, inverse tangent n over n cubed. Yeah, it's an alternating series. That negative 1 to the n it makes it alternating. Well, if I take the absolute value of each term, so absolute value of each term, that's going to give me the series it's going to give me that series. That's an interesting series to consider. So let's start with what we know. As inverse tangent heads off to infinity, we know what its graph looks like. We know the limit as n goes to infinity of inverse tangent is pi over 2. So that tells me, so let me write that down as a That tells me that inverse tangent of n is less than or equal to pi over 2. I could divide both sides of that inequality by n cubed. And over here on the right side, instead of writing this as divided by n cubed, let me just write it as this product. I think something's brewing here. I look at this and I say, well, the series 1 over n cubed, we know that's a p series. So we know it converges. P is 3. That tells me the series pi over 2 times 1 over n cubed. I know that series converges. Why? That's right. It's just pi over 2 times a known convergent series. Remember, multiplying a series by a constant doesn't affect the convergence or divergence. So now that I know this series converges, it almost looks to me like right here, I'm looking at that preamble for the direct comparison test. I know this series converges. I know this converges. So something that's smaller than it must also converge. So let me write that down. I now know this series converges. And why do I know that? Well, it's thanks to the direct comparison test. Direct comparison test with the series pi over 2 times 1 over n cubed. Since this series was nothing more than taking the absolute value of each term of this series, I immediately know, thanks to the absolute convergence theorem, I immediately know that this series converges. And since the absolute value of each term converges, that tells me this series converges absolutely. And that was number 59. So this is an important section to get these bigger ideas, absolute convergence, conditional convergence, under control. I know some people may look at this and they may tack it by first trying to do the alternating series test and to see that it converges. And then after they do that, it's like, well, I have to classify that convergence as conditional or absolute. And then they would have to do this to classify it. But notice, by initially starting this problem off by looking at the absolute value of each term, and we ended up determining that it converges thanks to the direct comparison test, that immediately told us that the original series converged absolutely. So that's it here for section, 10.6. So now you can head off to the exercises, the section 10.6 exercises, and do the exercises. Thanks for watching.